This is Lecture 13 in the Fiber Optic Association series of lectures on fiber optics. This one is about visual testing of fiber optics. Seeing what goes on in fiber optics can be difficult because the human eye is not sensitive to the infrared light that we use for transmission. It's invisible to most people, although some can see out in the 850 nanometer range. So what we do is we use visible light sources to view fibers, or we use a unique tool that allows you to see infrared light. Although our eye is not sensitive to infrared light, digital cameras are. The top photo you see here was shot with a digital camera, and the bottom was actually shot with a digital camera in a cell phone. You can use them to check for power in the fiber, to make sure it's safe, for example, before you inspect the connector with a microscope, or you can use them to trace fibers. There's a complete YouTube video by the FOA that shows how to do this. Be sure to watch it. One gadget everybody who works with fiber should have is a visual tracer. Some of them use flashlights like this one, some use LEDs, some use visible lasers. They're used to check fiber continuity and confirm polarity. That means that the fiber link connects a transmitter to a receiver. Polarity is often the first problem that people encounter when they're trying to connect fiber optic systems. A visual fault locator is a similar device, but it uses a higher powered red laser that has enough power that you can actually not only trace fibers, but you can see breaks or stress induced by bends in the fiber. It's really good, for example, for finding cracks that occur in fibers when they're placed in splice trays, or to find problems with patch cords. Another use for a visual fault locator is to optimize mechanical splices, or to use it with pre-polished splice connectors to optimize the splice in the connector itself. You simply attach a visual fault locator to the fiber, and the light that's lost in the connection will be a glow, a bright red glow, and you can minimize that and get the lowest possible loss from the splice. It's a simple process, been used for many years in fiber optics to great advantage. We also do visual inspection with a microscope. We look at the end of connector ferrules. When we're doing terminations, we use it to determine the quality of the polish on the connector end, or find scratches or cracks in the fiber, so that we might end up rejecting a connector. On any connector, we use it for looking for dirt or other contamination on the end of the ferrule. Typically, we use magnifications of about 100 to 400 times, and we use both direct and side illumination so they can show us different things about the end of the ferrule of the connector. Here's two views of the end of the same connector ferrule. The direct view with core illumination allows us to see if there are any defects near the core and to determine if the fiber is well aligned in the ferrule. But when we look at it with an angle view, either illuminating from the side or looking at the connector at an angle, we can see that this particular fiber has been chipped during the termination process and has epoxy residue on it. This is also a good method to look at connectors when you want to find dirt. Visual inspection will show you dirty connectors and show you how well you've cleaned them. Look at the size of the piece of dirt on this connector. It's almost as large as the 62.5 micron core of the multi-mode fiber. And there are other large pieces of dirt near the end of the connector. These come from exposure to the environment and actually from what people call dust caps, which at least one installer I know claims are called dust caps because they're usually filled with dust. We inspect the connectors with a microscope and clean them properly, then inspect them again to make sure they're properly cleaned each time we use them. On single mode connectors, we do another type of visual inspection using an interferometer. The interferometer can measure the end surface of the connector and actually determine the shape of the PC or physical contact finished dome of the ferrule. Interferometry is only used with single mode connectors generally, and it's only a lab instrument, not a field instrument. Interferometers show us three parameters of single mode domed polished connectors: the radius of curvature, the eccentricity of the dome, or is the dome centered on the fiber, and whether the fiber has been undercut during the polishing process. It's an extremely sensitive way of determining the quality of single mode connectors. The FOA has a number of other YouTube lectures, including many on fiber optic testing, as well as those on the basics of fiber optics, fiber optic components, fiber optic network design and installation. See our other YouTube videos, and of course, don't forget our online reference guide on the FOA website. We're the Fiber Optic Association, the Professional Society of Fiber Optics. On our websites, you'll find lots of technical information about fiber optics.